पवित्रवतु।
Good morning, everybody.
Good morning.
Today's video talk, I am going to teach you something about the probability theory. Okay, that is, you are going to learn some basic concepts or elementary probability theory. Okay, this session is divided into these 4 parts: prerequisite, basic definition and concept of probability, conditional probability, and independence of events will restrict to either 2 events or 3 events, and then some theorems, basic theorems, that is addition theorem, multiplication theorem, and base theorem. Okay. Now to learn probability prerequisite, I am going to talk on the factorial notation, fundamental principle, what do you mean by permutation combination, because in probability what is more interesting is how to determine the total number of exhaustive cases and total number of favorable cases. Okay, that is the principle of counting is very important. Suppose you are given an array of, say, a matrix of this 5 dots which consists of, say, 4 rows. Now how to count this? There is a shortcut. There are 4 rows and 5 columns. So total number of dots becomes 5 into 4, that is 20. So this is a shortcut. This is the counting principle. Am I right? That means you are not going to count 1, 2, 3, 4, 5 up to 20. You simply count the number of rows and the number of columns. So you will get 5 into 4, that is 20. So just see the first definition, the factorial notation. Factorial notation means the product of the first n natural numbers is called n factorial. Okay, n factorial is n factorial is 1 into 2 into 3 into 4 up to n minus 1 into n for n greater than or equal to 1, and that is equal to 1 for n equal to 0. That is the assumption. If n is equal to 0, n factorial is going to be 1. And since the product is commutative, the above product can also be written in the reverse order. Okay, n factorial is equal to n into, that is starting from n, you just go on reducing each term by 1 till you get n. Okay. So this is how we can write down n factorial as n into n minus 1 into 3 into. So the remaining terms n minus 1 into 3 into 2 into 1 can be written as n minus 1 factorial, or n into n minus 1, the remaining terms can be written as n minus 2 factorial, and so on. You can write n into n minus 2, n minus 3, n minus 4 factorial. Okay, you can reduce in the smaller numbers. That's the principle of counting. There are 2 basic principles. The first principle is principle of addition, and the second principle is principle of multiplication. These 2 principles are mainly used in the method of counting. So first I will give the definition, and with the help of example you try to understand the definition. If an event can occur in n or n mutually exclusive and alternative ways, then the total number of ways in which the event can occur is n plus n. In this I am considering only 2 events. You can generalize from any number of events. Okay, all these are dependent events, either this or this. Only one event can occur n. In that case, we can use the principle of addition. See, example is, let us suppose that you have 2 red shirts and 3 green shirts. Okay, 2 red R1, R2 and 3 green G1, G2, G3 shirt, and you want to select either red or green color shirt for a particular function. So how many different ways can this be done? Okay, either you select 2 red shirts or 3 green shirts. So you cannot wear 2 shirts at a time. You will wear only 1 shirt at a time. So only one event can occur at a time. Okay, so for red there are 2 possibilities, and for green there are 3 possibilities. So 2 plus 3 equal to 5 different ways we can wear these shirts. Okay, this is the principle of addition. Whenever word the or is used, we use the addition. Whenever word or is used, we use the addition. Okay, and this can be generalized for any number of words. Now consider the principle of multiplication. If an event has n possible outcomes and another independent, see this word is important, independent event has n possible outcomes, then there are m into n possible outcomes of two events occur together. These two events must be the independent event, then the total number of ways two events can occur together is n into n. I modify that example and just say how we get. Again we have two red shirts R1 and R2 and three trousers T1, T2, T3, and you want to select one red shirt and one trouser. That is the difference between the previous case and this case. In the previous case we use the word or, in this case we are using the word and. One trouser for a particular function, how many different outfits are possible. Okay, so this is the case. Now we are given two shirts and three trousers. Okay, that means with this shirt, independently you can wear either this or this or this. Independently. Okay. Similarly, with this shirt, you can wear either this or this or this. For each possibility of the first case, there are three other possibilities. Am I right? So the total becomes 3 plus 3, that is 6. Or it is somewhat like this. You will get this picture. Okay. So the total number of outcomes will be 2 into 3 equal to 6. That means if the first thing can be done in two ways and after it has been completed by any one of the ways, the other thing can be done in three ways. Then the total number of ways of doing both the things together is 2 into 3, that is 6. Is that okay? Few more examples we can consider here. There are 6 flavors of ice cream and 3 different cones are available. See, these two are different. Okay, we cannot independent things are there. Ice cream is different and cone is different. Okay, so with cone and ice cream we can form one combination. We can form one combination. So how many different single scoop ice cream can be ordered? So the first thing can be done in 6 different ways. Okay, suppose if you select a chocolate flavor. With the chocolate flavor, there are 3 different cones available. With the orange flavor, there are 3 different cones available, and so on. For each flavor, there are 3 different cones available. So with the first thing, you can do the other thing 3 different ways. So the total number of ways becomes 6 into 3, that is 18. Okay. So whenever word and is used, use the principle of multiplication. Okay. Here have one more example. 3 shirts. Now this is the extension. Instead of 2, I am considering 3. 3 shirts. 4 pants and 2 cats. So again all these 3 are independent. Okay. So the total number of different outfits will be 3 into 4 into 2, that is 24. And therefore this principle works only when all the choices are independent. Otherwise principle of addition is used when they are dependent. Is that okay? So after this we will go to permutation. What do you mean by permutation? Based on this factorial notation, principle of addition, multiplication, now I will define permutation and combination. Okay, I will explain with the help of example so that you will understand this definition. Okay, suppose there are 5 students. Suppose there are 5 students. Say S1, S2, S3, S4, and S5. And I want to select any 2 students to play a game of chess. I want to select any 2 students to play a game of chess. So how many different ways I can select this? How many different ways I can select this? So I will select S1 student. With S1 there is no point in selecting S1 again. I want 2 different students to play a game of chess. So I can select with S1 S2, or with S1 I can select student S3. With S1 I can select student S4. With S1 I can select student S5. Okay, again, either I select S2. With S2, there is no point in selecting S1 because that particular selection or that particular combination is already considered, so you will not get into it. So with S2, I can select S3. With S2, I can select S4. With S2, I can select S4. Okay, with S2, I can select S5. Am I right? On the similar line, with S3, I can select, now I will not consider S1, I will not consider S2, okay, I will consider S3, S4, am I right? S3, S5, is that okay?
Yes.
Am I, right? S1, S2, S1, S3, S1, S4, S5, S2, S3, S2, S4. I think this is I written 2 times. S2, S5, S3, S5. On the similar line with S4, I can select S5. Right? So how many selections or combinations are possible now? We count this: first selection, second selection, third selection, fourth, fifth, sixth, 7, 8, 9, 10. So there are 10 combinations of 2 students taken from 5 students. Taken from 5 students. In this, order of selection is not important. I can select either in S1, S2 or S2, S1. I can select a student in S2, S1 or S5, S2. There is no matter the order of selection. Such a selection is known as combination. So now I put in the mathematical form, from 5 students, any 2 students can be selected in 10 different ways. Or there are 10 combinations possible from a group of 5 students, from a group selected 2 students from a group of 5 students. Now mathematically it is written as like this: total number of combinations, total number of combinations or selections is given by 5C2. This is the notation 5C2, or some authors use this notation 5C2. Okay, this by calculating we got the answer 10 ways. Okay, now in general, if you are given n objects, n different objects, from n different objects, r objects can be selected, in which the order of selection is not important, is denoted by NCR. Total number of combinations, NCR, is given by the formula n factorial divided by r factorial into n minus r factorial. Okay, obviously we are selecting r from n, therefore we have condition r must be less than or equal to n. So this is about the combination. Now let's slightly modify this problem. And this way, select any 2 students, and for the first student you give rupees 5 and second selected student give rupees 10. Have you understood? Select first student and give rupees 5, select second student, give rupees 10. Okay, it means that now the order of selection becomes important. If I select in the order say S1, S3, student S1 will get rupees 5, student S3 will get rupees 10. But if I select in the order S3, S1, student S3 will get rupees 5, student S1 will get rupees 10. So the order of selection is important, the order of arrangement is important, or the arrangement of selection is important. Okay, so whenever order is important, we use permutation. Okay, so for each of this combination, either S1, S2, or you will have S2, S1. Similarly, either S1, S3, or you will have S3, S1. Okay, so these 2 are different now. These 2 are different because the order of selection is important. That is known as permutation. So from 5 objects, now you put here. From 5 objects, any 2 objects can be permuted, or can be arranged in 5P2 ways. And you will get this answer 20. Okay. In general formula is from n objects, any 2 objects, any r objects can be arranged in NPR ways. Or this NPR is nothing but total number of permutations, or arrangement. Total number of permutations or arrangements. So this is given by the formula n factorial divided by n minus r factorial. Again, r is less than or equal to n. Is this clear? Now this permutation is of linear permutation, arranged linearly. There are 2 types of permutation. Either you have linear permutation or circular permutation. Okay. In the round table conference, the delegates are sitting on the round table. So how many different ways can be arranged? So I give the direct formula. If there are n objects, they can be arranged circularly in n minus 1 factorial. Okay. If you have given n objects and you want a linear arrangement or linear permutation, the total number of permutations are n factorial. n objects can be arranged amongst themselves linearly in n factorial ways, but n objects can be arranged amongst themselves circularly in n minus 1 factorial ways. Okay, so that is it. Permutation is an arrangement in a definite order of number of objects taken sum or all at a time. There are two types of permutation: linear permutation or circular permutation. Okay. So linear permutation of n different objects taken r at a time is the total number of ways in which n objects can be arranged at r places in a line, denoted by these are the different notations NPR or NPR or this. Okay, and the formula is given by NPR is equal to n factorial divided by n minus r factorial. Okay, circular permutation of arrangement in circle are called circular arrangement, and total number of permutations is given by n minus 1 factorial. Okay, so this is about the permutation. Now just see the combination definition. Okay, whatever I explained, that is just put over here. Combination is a selection. Combination is a selection which can be made out of the number of things by taking some or all at a time. Order of selection is important. So whenever you are given the problem, you try to understand whether the order is important or not. Whenever order is important, go to permutation. Whenever order is not important, go to combination. Okay. So the total number of combinations is given by the formula NCR is equal to n factorial divided by r factorial into n minus r. Is that okay? So this is the prerequisite required for the purpose of studying the probability. Now we will study basic definitions to develop the probability theory and then the meaning. Okay. So basic concepts. So now what do you mean by probability? Probability means a chance. See, in the everyday day-to-day life we perform large number of experiments. There are two types of experiments. In physics, chemistry, you perform the experiments where the outcome is unique. Outcome is unique, they are certain. You put a water on the gas, it will get vaporized. That means outcome is known to you. Okay, outcome is known to you. There are certain experiment. But there are so many experiments in which the outcome is not sure. The set of outcomes you know to in advance, but exact outcome you will come to know only after conducting the experiment. Only after conducting the experiment. Suppose if I throw a die, okay, you know that you will get either number 1 or 2 or 3 or 4 or 5 or 6 on the uppermost face of the die. But exact outcome when you will come to know? When you throw a die. Okay, so throwing a die is a random experiment. Throwing a die is a random experiment. So best definition is random experiment is an action in which all possible results of the action are known in advance. This is very important. All the outcomes are known in advance. The exact result is unpredictable. That is not known in advance. Okay. So whatever result you get, that is known as the outcome. Okay. Outcome of that random experiment. If the outcomes, all the outcomes are equal chances, then it is known as equally likely outcomes. Okay. Equally likely outcomes. Outcomes of random experiments are said to be equally likely if none of them are expected to occur in preference to other. The very simple example is throwing a coin. When you throw a coin, we will not give more preference to the occurrence of head, or will not give more preference to the occurrence of tail. We will give the equal chance, okay, to occurrence of head and tail. So these outcomes are equally likely. Okay, when you throw a die, all the numbers are given the equally likely to occur. So that is equally likely outcomes. Sample space. Now the set of possible outcomes. After conducting the random experiment, you will get the different outcomes. That set of distinct possible outcomes is called as a sample space. Simple definition. Is that okay? It is denoted by, since it is a set, it is denoted by S. Okay. So for example, if you throw so my random experiment is a coin is tossed. Okay. So either I will get head or I will get tail. Either I will get head. So these two possible outcomes I know in advance. exact outcome I don't know. Therefore, this is a random experiment, and this set of possible outcomes is the sample space which I am denoting by S. Now, how many outcomes are there? How many elements are there in the set? There are two elements. That is how we write in set notation and S. Number of elements in the set S. Number of elements in the sample space S is equal to 2. Okay. Now suppose instead of 1 coin, 2 coins are tossed. 2 coins are tossed. What are the possible outcomes? On the first coin you will get a head. Second coin also you will get a head. This is one possible outcome. On the first coin you will get a head. Second coin you will get a 10. Or on the first coin you will get a 10. Second coin you get a head. On both the coins you will get a 10. See, these two outcomes are different. Order is important here. Okay, first coin you will get a head. Second coin you will get a 10. Or first coin you get a head 10. Second coin gives a head. So these two outcomes. So total number. These are the possible results or outcomes of this experiment that will come to know only after conducting the experiment. Therefore, this experiment is a random experiment. This set of possible outcome is a sample space for this experiment. This is denoted by S. How many outcomes are there? There are 4 outcomes. So we write this and S, number of elements or number of outcomes in the sample space S is equal to 4. Okay, so that is 2 square. That is 2 square. So in general, if n coins are tossed, total number of outcomes will be 2 raised to n. Okay, so this you can generalize for the dice also. Okay, 2 dice are thrown. You know that total number of possible outcomes are 36. On the first die you get number 1, second die you get the number 1, first die you get the number 1, second die you get the number 2, and so on. So you will have 36 outcomes, distinct possible outcomes. If n dice are thrown, you will have 6 raised to n possible outcomes. And if you can count the outcomes, then it becomes a discrete sample space. Here I can count how many elements are there. Therefore, all these are discrete sample space. Okay. Here one more example is there. If you want to go through that. It's slightly different example. A coin is tossed twice. Okay. If a second row results in a head, a die is thrown. Otherwise, coin is tossed. Write the sample space. Have you understood this? Let us conduct this experiment. Coin is tossed twice. So assume that first time you get a head, second time also you get a head. Okay. So what is the condition here? If the second row results in a head, you have to throw a die. So what are the possible outcomes you will get? Either you will get number 1, or you will get number 2, or you will get number 3, and so on. You will get number 6. If the second row is a head, these are the possible outcomes. Or this is on the first time you get a tail. Again, second row you will get a head. Again, you apply that logic. If the second row is a head, die is thrown. So again, you will get number 1, or you will get number 2, or you will get number 6. Am I right? These are the possible outcomes. Now suppose if I have L, but the second row is 10. So what is to be done? If this otherwise coin is tossed. Since it is a 10, so now you toss a coin again. So on the coin, either you will get a head or you will get a tail. Or you may have this type T, H or T. So this set of possible outcomes for this experiment is the sample space S. Okay. So try to understand the experiment, conduct the experiment logically, and first to write down the total number of exhaustive cases, total number of outcomes, which is very important in case of drawing. Okay. So this is what we get. Sample spaces. Is that okay? Now sample space. Now consider the event. Any subset of the sample space is called event. Event means, dictionary meaning of event is whatever happens, that is called event. Happen means you are getting the outcome. You are conducting the experiment and you are getting the outcome. Obviously that outcome is a part of the sample space. Part of the sample space may be considered as a subset of the sample space. It is a subset of the sample space, and therefore how we define event? Any subset of the sample space is called event. Is that okay? Any subset of, that is, occurrence of favorable outcomes from the given sample space is the event. For example, if you throw a set back, sample space is 1, 2, 3, 4, 5, 6. Okay? And if I define the event that dash shows a number greater than or equal to 4. Dash shows a number greater than or equal to 4. So conduct the experiment. If you get 4, that event has occurred. If you get 5, that event has occurred. If you get 6, that event has occurred. Okay, so that is known as the occurrence of the event. If you get a number 1, that means event does not occur. Non-occurrence of the event. If you get a number 2, non-occurrence of the event. Okay, so you get the outcome which is defined in the event, we call that occurrence of the event. Otherwise, it is called as the non-occurrence of the event. Okay, since it is a subset of the sample space, I hope you know this notation. A is a subset of the sample space, and therefore obviously the number of elements in the event are always less than or equal to the number of elements in the sample spaces, and they cannot be negative, and therefore 0 less than or equal to n, less than or equal to ns. Okay, is that clear? Event. And there are different types of event: elementary event, mutually exclusive event, exhaustive event, sure event, impossible event, complementary event. Okay, I'll define one by one. Elementary event or simple event means any sample space, any event which contains a single point is called elementary event. Okay, and event consisting of single point of the sample space is called simple or elementary event. Okay, simple example. Consider the same random experiment. A die is thrown. Sample space is 1, 2, 3, 4, 5, 6. Now I define the event. Let us denote the event by A, that die shows an even prime number. Die shows an even prime number. So what is that? That is 2. Okay. So that event contains only one sample point, one outcome, which is 2, and therefore that event is a simple event or elementary event. Okay. If you consider only one event and form the subset, so each of the sample point becomes an elementary event. Each of the sample point becomes an elementary event. Okay. So that is what I am written here. Every sample point of the sample space forms an elementary event. This statement is very important. Every sample point of the sample space forms elementary event, which develops the definition of probability using axiomatic definition of probability. Okay. Next. Already I have defined what you mean by occurrence or non-occurrence of the event. Okay. Conduct the experiment, you will get the outcome which is defined in the event, then we call it as a occurrence of the event. Otherwise, it is called as a non-occurrence of the event. Then sure or sure event, impossible event, complementary event. Sure event is that is bound to happen. That is bound to happen. In case of throwing off a die, if I define the event, die shows a number less than or equal to 6. Yes, it is obvious. Less than or equal to 6. Okay, it is obvious, right? Therefore, it is a sure. But instead of that, if I define die shows a number multiple of 7, which is not possible, so that is an impossible event. It does not contain any sample point. It does not contain any sample point. Okay. Now complementary event. I define the complementary event with the help of example. Take the same random experiment. A die is thrown. So the sample space, as you know that, it is 1, 2, 3, 4, 5, 6. Okay. So now I define the event that number on die is less than or equal to 2 or less than or equal to 3. Number on a die is less than or equal to 3. So what are the possible cases you will get? Either 1 or 2 or 3. Okay. Now we consider the set of elements. We will consider the set or subset of elements which belong to the sample space S but does not belong to the A. Which belong to the sample space S but does not belong to the event A. What are those elements? Those elements are 4, 5, 6. These elements belongs to S but does not belong to A. Such a set is called complementary element. Such a set is called complementary element, which is denoted by A dash or AC. Okay. So how will you write down this statement? Number on die. Take the complement of this opposite sign. Instead of less than or equal to, you take greater than 3. You will get a complementary. Okay. So in mathematical notation, A dash or AC is the set of X. X is the element. This complementary set contains the element X such that this element belongs to the sample spaces. This element belongs to the sample spaces, but it does not belong to the given event A. Okay, that is known as the complementary. So that is the definition. Is that okay? Algebra of the events. Instead of considering only one event at a time, now consider 2 or more events. 2 or more events. So that means let A union of 2 events you can consider, intersection of 2 events. In general, you can consider union of n events, intersection of n events. We will restrict ourselves to 2 events. Okay. Let A and B be any 2 events defined on the sample spaces. Then the union of 2 events, joining of 2 events, is denoted by A union B and is defined to be the occurrence of at least one event. Either event A occurs or event B occurs or both occurs. So that is A union B is the set of X such that X belongs to A or X belongs to B or X belongs to both. I will explain this with the help of example. First just go through this. Intersection of 2 events. So again we define any 2 events on the sample spaces. Their intersection is denoted by A intersection B. This is the symbol A intersection B, or simply you write AB. And it is defined as the simultaneous occurrence of the 2 events. That is the difference between union and intersection. In the union, we use the word at least one. In the intersection, we use the word simultaneous occurrence of both the events. Okay. So A intersection B is the set of X such that X belongs to A and X belongs to B. So here the word is and, here word is not. Okay. So usually addition principle which I give you is used for the union of 2 events, and the multiplication principle is used for the intersection of 2 events. Okay. So just see the example for this. Consider the same random experiment. Okay. Let us define the event A, that number on die is less than or equal to 4, and event B on the same sample space you defined. Okay, do not use some other sample space and try to combine them. Okay, on the same sample space, number on die is greater than or equal to 2. Greater than or equal to 2. So what is the set A? What are the possible outcomes? Less than or equal to 4. 1, 2, 3, 4. And here what do you get? Greater than or equal to 2 means 2, 3, 4, 5, 6. Is that okay? Now consider A union B. Joining of 2 events. A union B. That means we will consider the sample point which belongs to A or which belongs to B or both. Or both. So let us consider the first. This belongs to A. So write down all the sample points which belongs to A. Now consider the sample points which belongs to B. Now 2 is already considered. 3 is already considered, 4 is already considered. So those points we will not consider because they are occurring in both. So that third point or both is solved. Now what are the remaining point? 5 and 6. Okay? So this is A union B, joining the 2 events. Now in this case we are getting this as the sample space. It is not necessary always. It is not necessary. In this case we are getting A union B is the sample space. If this is the case, if A union B is the sample space, we call it as a we call it as a exhaustive test. If this is equal to S, we call it as an exhaustive test. It is not necessarily always that we will get the exhaustive. What is A intersection B? That is common. See that expression. A intersection B is what? X belongs to A and X belongs to B, and it should be the element of both the sets. So if you consider 1, it occurs only A, so we will not consider 2. This occurs here as well as here. 3, 3, 4, 4. So this 3 outcomes are A and B. Therefore, that is A intersection B. 2, 3, 4. Is that okay? So, how many elements are there? There are 3 elements. In this case, there are 6 elements. Is that okay? Next, mutually exclusive and exhaustive events. Okay, 2 events A and B defined on the sample space are said to be mutually exclusive if they cannot occur together in a single trial. Occurrence of one event prevents the occurrence of the other event. If you throw a die and A is the event that die shows a even number and B is the event that die shows an odd number, so if you get a number 2, that means event A has taken place, event A has occurred. It suppresses or it prevents the occurrence of the other event B. You can get A or B, not the 2 events at a time. Not the 2 events at a time. Such events are said to be mutually exclusive event. Okay? Exhaustive events. 2 events A and B are defined on the sample space. If A and B is equal to S, just now I did the example, you will get a complete sample space, then that is known as exhaustive events. Okay? So, if they are exhaustive as well as mutually exclusive, then they are said to be complementary. You can see that these 2 events are complementary. That means the elements which occur here, in this case what? A intersection B is not a null set. If A intersection B is the null set, then they are mutually exclusive, they are complementary. Mutually exclusive events and exhaustive events. Mutually exclusive event, nothing is common. Okay? Then they are said to be complementary. By using this definition, now we can define the problem. These basic definitions: event, sure event, impossible event, mutually exclusive event, exhaustive events, complementary event. Based on these definitions, now we can define the probability. See the probability. Now, probability can be defined in 3 different ways. There are 2 approaches basically: objective approach and the subjective approach. There are 2 approaches: objective approach and subjective approach. In objective approach, it can be defined either classical or empirical or axiomatic definition. Okay, classical means using previous information, prior information, we define the probability. Empirical definition means actually gives the estimate of the probability. That means you conduct the experiment and determine the value, which gives the estimate of the probability. And some examples are based on that we define, that is known as axiomatic definition of probability. Okay, these are very simple. So define the classical definition first. Okay, this definition was given by the Laplace, and the most important thing is this is applicable only when the outcomes are equally likely. Okay, so the definition is somewhat like this: if an experiment can produce an mutually exclusive and equally likely outcomes. I hope you remember what I mean by equally likely. Okay, that is a very important thing in this case. Equally likely outcomes, out of which n outcomes are favorable to the occurrence of the event A, then the probability of A is denoted by P bracket A, and it is a ratio n upon n. Okay, number of favorable cases divided by total number of exhaustive cases. Now, this both numerator and denominator we know from the previous record. So, from the past we are calculating this probability. Therefore, this is also known as prior definition of probability. Okay, if you are given the unbiased coin, then you know that there are only 2 possible outcomes, out of which one is head and other is tail. So, prior information is known to us. So, the probability of getting head is half. This is known as classical definition of probability. This is calculated using the classical definition. Okay, when die is thrown, okay, total number of exhaustive outcomes we know already in advance, that is 6, and probability of getting any number is 1 by 6. Okay, so that also we know in advance. So, example for this is 2 dice are rolled. Let us define the event E as a set of possible outcomes where the sum of the numbers on the faces of the 2 dice is equal to 4. Find the probability. So, in this case, what happens? 2 dice are rolled. We know all 36 outcomes in advance. We know all 36. So, prior information is known. Now, from these 36 outcomes, you select only those outcomes for which the sum is equal to 4. So, what about possible cases? 1, 3. Am I right? 2, 2. And 3, 1. So, there are only 3 possible cases. So, out of 36, 3 cases are favorable for the occurrence of this event. So this information we know from the past record. Therefore, the probability of E is 3 by 36. So that is the first level. The prior definition or classical definition. Then after this we have empirical definition. The empirical definition means experimental. You conduct the experiment and try to obtain the problem. You are given a point which is not an unbiased point, or you are given a time which is not an unbiased time. Then how to determine the probability of getting head or probability of getting any number on the uppermost first order? You go on conducting the experiment. You toss a coin, okay, say 100 times, 1000 times, okay. So conduct the experiment, and out of say 1000 times, suppose you get 300 times head. It means that the probability of getting head is 300 divided by 1000. Is that okay? So conduct the experiment. So this is the estimate of the probability. This is known as the empirical definition of probability. Okay, so the empirical probability or experimental probability estimates the probabilities from the actual experiment. In statistical term, empirical probability is an estimate or estimator of the probability. So I want to know the probability of how many persons like red color. How do you determine this? You have to conduct the experiment. You go and ask each person which color you like most, which color you like most, which color you like most. Say you take 1000 persons, and out of that 1000 persons, suppose there are, let's say, 400 persons who like the red color. So the probability is 400 divided by 1000. So this is the estimated probability. This is the estimated probability, or that is known as experimental probability or empirical probability. So this is how we can obtain. So 30 people were asked about the color they like, and so this is the result. Okay. So if a person is selected at random from the above, from a group of 30, what is the probability that this person likes the red color? What will be that? 10 by 30 from that. So this is calculated using the frequency or by conducting the experiment. Therefore, that value is known as the empirical probability or experimental probability or estimate of that probability. Is that okay? Now consider axiomatic definition of probability. It is based on this of axioms. Okay. Suppose any event defined on the sample space S. Okay. First axiom is that for every event E in S, you take any event, whether it is a simple event or composite event. Okay, whether it is a simple event or that value, that probability value is always greater than or equal to 0. It must be positive. Total probability of S. Sure event, probability of the sure event is 1. And for any two mutually exclusive events A and B, mutually exclusive event means A intersection B is the null set in the sample spaces. Probability of A union B is equal to probability of A plus probability of B. So based on these three axioms, we define the probability. So that is known as axiomatic definition of the probability. And all these probability definitions always lead to the simplest form, number of favorable cases divided by total number of exhaustive cases. Is that okay? So this is the concept. Now let us consider, based on what we are considering, only the simple probability, probability of any event A, or probability of any event B, or probability of A union B, or probability of A intersection B. This is the problem. Now let us define the conditional probability or independence of the rules. Conditional probability. Let S be the sample space associated with the random experiment. A and B be any two events defined on the sample spaces. Then the probability of occurrence of event A under the condition that event B has already occurred, such that probability of B is not equal to 0, is called conditional probability of event A given B, and it is denoted by P bracket A slash B. That is the conditional probability. Okay, under the condition we are obtaining the probability. For example, consider a pack of 52 cards. Okay, one card is drawn. One card is drawn at random, and you are given that it is a hard card. You are given that it is a hard card, and we want to find the probability that it is a face card. It is a face card. So we are finding the probability of face card under the condition that hard card is drawn. So such probabilities are called conditional probability. Is that clear? We are finding the probability of getting a face card. I hope you know the face card: king, queen, and jack. They are known as face card. Okay, so we are finding the probability of getting face card under the condition that it is a hard card. Okay, so this is how we can put. Our experiment is a card is drawn from a pack of 52 cards. Okay. So you know that NS is equal to 52C1. Apply the combination, and 52C1 is 52. Now we want to find the probability that face card is drawn. Face card is drawn under the condition. So that condition I put using the slide. Under the condition that hard card is drawn. Okay. So logically it's very simple. You are given that hard card is drawn. So we will not consider all 52 cards. We will not consider all 52 cards. Our sample space reduces to only hard cards. There are 13 hard cards. So our sample space reduces to only 13 cards. Such a sample space is known as reduced sample space or truncated sample space. So sample space total number of outcomes will be 13. 13 hard cards. Now in these 13 hard cards, how many are face cards? There are 3 face cards. So the probability is 3 by 13. This is known as conditional probability. This is known as conditional probability. There is assumption that this is denoted by A, this is denoted by B, this event is denoted by A, this event is denoted by B. So the probability of A given B is 3 by 13. It's very simple. Logical thinking. Instead of considering all 52 cards, you consider only 13 cards. Out of these 13 cards, only 3 cards are favorable for getting the face card. Therefore, probability of A given. Probability of event A under the condition that event B has already occurred is 3 by 13. Now let us try to derive the formula for this. Okay, what is this? 13. 13 is the number of hard cards. Number of hard cards. That is this. Number of elements in B. Number of elements in the B. Number of elements in the B. And what is this 3? 3 they are the face hard cards. They are the face hard cards. So both the event occurs. Okay, so that is an A intersection B. So this is what formula you will get. Okay, probability of A given B is NA intersection B upon NB. We assume that this NB is not equal to 0. Denominator is not equal to 0. Either you put in this form, we can put in the probabilistic form. Just divide both numerator and denominator by NS. You will get the required answer. That is N A intersection B upon NS divided by NB upon NS. Is that okay? So by definition of probability, this is the total number of existing cases in the sample spaces. Out of these are favorable for the occurrence of A intersection B. So using the classical definition of probability, this is nothing but probability of A intersection B. And again, this is the probability of, assuming that probability of B is not equal to 0. Such probabilities are called conditional probability. Or you can put other way format, probability of B given A is N A intersection B divided by NA, or divide both numerator and denominator by NS, you will get probability of A intersection B upon probability of A, assuming this denominator probability of A is not equal to 0. Okay. We can prove this result using Venn diagram also. This is the sample space S, and these two events are defined. Event A and event B. Okay. Let us try to determine probability of A given B. Let us try to determine or derive the formula for probability of A given B. You are given that event B has occurred, event B has taken place. So we will not consider it as sample space. We consider only this circle. We consider only this circle because event B has occurred. We consider only this. Now in this event B, we want the occurrence of the event A. We want the occurrence of the event A. So event A occurs only in this portion. Event A occurs only in this portion. So out of so many sample points, that is out of NP sample points, only and A intersection B sample points are favorable for the occurrence, and therefore conditional probability of A given B is any intersection B upon N. This is the simplest proof. Is that okay? So that is the probability of A. This is conditional probability. We can define the theorem. Probability of A intersection B is probability of A intersection B upon probability of B. Probability of B is not equal to 0. Probability of A is not equal to 0. Okay. Various examples can be considered. Just now I get this. A card is drawn from a pack of 52 cards. Given that it is a red card, what is the probability that it is a face card? Okay, so now our sample space reduces to only red cards. How many red cards are there? 26. 26. Out of 26 red cards, how many are face cards? 6. So 6 by 26 is the required. Okay, that is required 13. Okay. A pair of dice is rolled. If at least one die shows the number 5, what is the probability that sum is 11? So what is the condition? Pair of dice is drawn, total number of exhaustive cases are 36. But now you have given the condition that at least one number shows, one die shows number 5. So you will have outcome either 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, 5 or 5, 1, 5, 2, 5, 3, 5, 6. Okay. So total 11 outcomes will be there. Total 11. Out of these 11 outcomes, only 2 outcomes are favorable for getting sum 11. 5, 6 or 6, 1. So the probability is 2 by 11. Okay. So that is the required. Now consider addition theorem. Okay, let S be the sample space associated with it. Now we use the addition principle of addition to solve probability of A in and B. S be the sample space associated with the given random experiment. A and B be any two events defined on the sample space. Then the probability of occurrence of at least one event, either A or B, that is at least one event, is denoted by probability of A in and B or probability of A plus B, and it is given by the formula probability of A in and B is equal to probability of A plus probability of B minus probability of A intersection B. This can be proved using Venn diagram. Okay. So card is drawn from a pack of 52 cards. What is the probability that it is a king card or queen card? Okay. So or means addition here. Or means addition. King card or queen card. Is that okay? Then let us do the multiplication. I just gave the statement. Okay, multiplication theorem is given by. It is based on the principle of multiplication. So S be the sample space associated with the random experiment. A and B be any two events defined on the sample spaces. Then the probability of occurrence of both the events is denoted by probability of A intersection B or probability of A B. These are the different notations. Okay. So it is given by the formula probability of A into probability of B given A or probability of B into probability of A given B. From this result, you just adjust the term, you take this term to the left hand side, you will get a probability of A intersection B. And the last one is the base theorem. This is very important in the probability, which is nothing but a conditional probability. It is based on the conditional probability. Instead of two events, suppose you have given and mutually exclusive and exhaustive events. You are given and mutually exclusive and exhaustive events, and one more event which occurs. So we want to find the posterior probabilities. Let E1, E2, E3, En be the set of n mutually exclusive and exhaustive events defined on the sample spaces of a random experiment. Let A be any arbitrary event defined on the sum. So all this information, prior information we have given to you, probability of A is not equal to 0. Then the probability of EI when the event A has actually occurred. So this is known as the posterior probability. What is the probability of EI when the event A has actually occurred is given by conditional probability of A intersection BI upon probability of A. Okay, and this definition is based on the conditional probability. If mutually exclusive exhaustive event means what? Or you put this in the terms of diagram. This is what is the sample space S. Okay. So, but this is the subset. Consider these subsets. Each subset that is denoted by, suppose this is E1, this is E2, this is E3, this is En. All these subsets are nothing but events defined on this sample space S. So nothing is common in these events, and if you join all this, you will get a sample space. Therefore, this represents E1, E2, E3, En, mutually exclusive and exhaustive events. Or using the notation, this is nothing but E1 union E2 union E3 union En is the sample space S, and E1 intersection E2 or En intersection EJ is the null set. So that means they are mutually exclusive and exhaustive events. Okay. So I will give one example for this. A doctor is called to see a sick child. A doctor is called to see a sick child. Doctor has prior information that 80% of sick children in that area have the flu, while the other 20% are sick with measles. Okay. So these are the two events defined. Either they will have a flu or measles. Okay. Let E1 be the event that selected child, which is a sick child, have a flu, and E2 be the event that he has a measles. So probability of E1 is 0.8. Probability of E2 is 0.20. This information, prior information is given to you. Now, there is no other disease. That means either this or this. Nothing is common. So, these two events are mutually exclusive and exhaustive. If you combine these two, all these children, you will get the entire population of sick children. Well-known symptoms of measles is rash. From the past record, it is known that chances of rashes during that sick child is suffering from the measles is 0.95. One more event is defined. Rashes. Okay. So you are given that probability of E1 is 0.80, probability of E2 measles is 0.20. Since they are mutually exclusive, so total probability is 1. Total probability is 1. That is important. And you are given another event, that the rash event. So probability that selected child has a rash, given that he is suffering from flu. That is given to be 0.95. Okay, and again selected child has a rash, given that is suffering from the measles, that probability you are given 0.02. So all these prior definitions are given. What is the required probability? How we put that required probability? What is the probability that selected child, am I right? Upon examining the child, doctor finds a rash. We are given that doctor finds a rash. So event A has given to you. What is the probability that he has a measles? That is, this is the probability we have to give you. So using that formula, we will get a required answer. Is that okay? So that completes this concept of probability. Okay. The detailed notes are available on this website. Okay, you can go through the number of solved problems, unsolved problems with the answers are given in these notes. Okay, that is the Somaiya.edu Vidyavihar/KJSCC academic department /47/statistics. This is the link where these notes are available. Okay, thank you very much.